this video is all about what makes a good leaving group. What makes a good leaving group? If you looked at some of the previous examples we've done on substitution reactions, these have all been reactions where we're starting with something that looks like an alkyl halide. Remember, alkyl halides are molecules where we've got an alkyl group which is attached to a halogen. And in our case, the halogens have usually been things like bromine, chlorine, or iodine. And when we're treating our alkyl halide with some kind of nucleophile, we're getting a new nucleophilic substitution product. So in this case, we're treating with the cyanide ion, and we're getting a new substitution product, and we're kicking off one equivalent of our bromide ion. This is our leaving group. Okay, and remember, this is our nucleophile CN, and so why haven't we seen any examples yet where we take, instead of using bromine all the time, well, alcohols are pretty common in organic chemistry. Why can't we take an alcohol and do the same type of reaction? So why can't we just do that, for example? We'd get C triple bond N here, and we'd displace OH minus. Or for that matter, why can't we just take butane? Just butane, where we have just 3 hydrogens on the butane, and just treat that with C triple bond N. And then we would get 1, 2, 3. We'd get our C triple bond N attached here. And I guess that would mean that we'd have to displace a hydride. So we have carbon, hydrogen, hydrogen, hydrogen. So we'd be losing a pair of electrons, would be going to the hydrogen here. We would get H dot, H lone pair. Okay, so why is it that we see this reaction happen all the time, and yet this reaction we never see, and we especially never see this reaction? So we don't see this reaction, and we especially never, ever, ever see this reaction. Well, it has a lot to do with the fact that we're changing the leaving group. So in this first example, our leaving group is Br minus. In this middle example, our leaving group is OH minus. And in this final example, our leaving group is H minus. So why is it that the Br is a good leaving group and the OH is a bad leaving group, and H minus is just a terrible, terrible leaving group? Well, here's the key point about what makes something a good leaving group. It turns out that good leaving groups are weak bases. Weak bases. And if you think back to what makes something a weak base, it's something that's fairly stable by itself, right? Something that's fairly stable by itself. Br minus is a very weak base. And you think about strong bases, well, sodium hydroxide should be very familiar to you as a strong base in chemistry. And the hydride ion, H minus, is even a stronger base than that. But let's say you don't know off the top of your head what the different basicity values of all these different things are. And so let's say you wanted to find out, like, how do you know? Like, how do you know, or how do you look up whether something's going to be a good leaving group or not? Well, there's something called a Pka table. So I've drawn it up, an example of a Pka table here, and also put some examples of good and bad leaving groups here. And if you sort of start at the top of the Pka table, remember that our strongest acid is, one of the strongest acids you'll encounter is hydroiodic acid, HI. And the stronger the acid, the weaker the conjugate base. So as it turns out, a really strong acid, HI, has a very, very weak conjugate base, I minus. And similarly, HBr and HCl, we get the weaker acids and become better and better leaving groups. So our weak leaving groups so Br and Cl are not quite as good leaving groups as I minus, but they're in the same ballpark. So in this area here, this sort of top area of the Pka table with all our strong acids here, the conjugate bases of all of our strong acids are very, very good leaving groups. So we've got I minus, Br minus, Cl minus, water. And this one here, which is interesting, which we'll talk about later, this is called para-toluene sulfonic acid. And this is the conjugate base of that, which is sometimes known as the tosylate anion. And you'll encounter this later on when we talk about how to make alcohols into good leaving groups. This is an excellent, excellent leaving group. Now, one exception among the halides is fluoride ion. It tends not to be a very good leaving group. You won't see this as a leaving group in organic chemistry for the most part, especially in substitution reactions, because it forms nucleophilic substitution reactions, because it forms very strong bonds, and it's a poor leaving group. In the moderate range, okay, as we go from our strong acids down here, these are sort of our weak acids, so carboxylic acids and protonated amines, and the conjugate bases of these they're not as good leaving groups as the previous examples, but they're okay. I mean, this is the acetate ion, and this is ammonia. This is an okay leaving group. And then as we go further down the table, we get to our weaker and weaker acids. So water only has a pKa of about 16. So its conjugate base is the hydroxide ion, which is a pretty poor leaving group. It's a strong base, and the same goes for alcohols. So CH3OH, the conjugate base of that is CH3O minus. It's a pretty poor leaving group. And then we get down into even weaker and weaker acids, which means that their conjugate bases are stronger and stronger bases. So amines, so NH2 minus is a very, very bad leaving group, as is H minus, and is an alkyl anion. So these are extremely poor leaving groups. You'll never see these as leaving groups. So there's really just 4 categories. There's excellent leaving groups, moderate, poor, and extremely poor. And the Pka table is really your friend when it comes to figuring out what makes something a good leaving group. So let's just make sure we get this in focus here. So your good leaving groups are things like Cl minus, I minus, Br minus, also water. Water is a good leaving group. So tosyl, so the tosylate anion is a good leaving group. So that is, actually it's O-tosyl. So looks like this. O minus, that's a good leaving group. Your moderate leaving groups are things like the acetate ion, which looks like that. NH3 is a moderate leaving group. Your poor leaving groups are things like hydroxide ion, OCH3 minus. Those are both poor leaving groups. And things that are terrible leaving groups, things that will never leave, are hydride ion, and for our purposes, NH2 minus will never leave. And also just alkyl anions. So for example, CH3 minus. Actually, let me redraw that. It's a little skanky. Alright, CH3 minus. So these are the 4 basic categories of leaving groups in organic chemistry, and pay special attention to those things that are very good leaving groups, because these will come up a lot in not only substitution reactions, but subsequently when we start talking about elimination reactions. So keep these leaving groups in mind.